Sorting is our second algorithm we're going to talk about. And both of these are pretty, widely known. Everybody uses both of them at some point in their lives. So there's been a lot of research into them. And there's been a lot of research into making them efficient. So it's really well known. And if you can improve the order bounds on sorting, right, you can at least become famous, if not rich. I don't think you get rich from mathematics, and this is essentially a mathematics operation. But maybe, right? So we're gonna look at some different algorithms to do insertions, and we're gonna look at how the algorithm can either make things take a long time, like insertion sort, like the dance we just saw, or make things go a lot faster by using something like a merge sort. So we're going to look at this in two different ways, and I want to bring up first. Let's look at my handy dandy notebook. Going to look at Lecture21 test sort. This is in Lecture21 files, I think it is, on SMITI downloads page. We're going to look at our algorithms in two ways. We're going to analyze them, at least do some hand-wavy informal analysis to show you that it's insertion sort is order of n squared, and merge sort is order of n log n. But it's going to be a little hand-wavy, just because we haven't developed the computational tools yet. You'll get a lot of that in data structures. But the other way we can look at these is we can look at these using experimental. And that's what you guys were doing in your labs, right? You were looking at algorithms and how long they take to run, and kind of, and doing that to compare them. So this is our function to look at our sorting functions and see how long they take to run. So we have, this is our major algorithm. This is our algorithm that's going to run in time our sorting algorithms, or this is our function that's going to run in time our sorting algorithms. It has 4 parameters. The first parameter is just what to call it so that we can print out something cool, like merge sort or insert sort. The second is actually passing a function in by as a parameter. So this is the actual function that gets called, right? So you can see down here, we use it just as if it were a function, right? We give it a parameter, and this v is going to be an unsorted list, and then known v is going to be a sorted list, and known v is just going to let us do a comparison to see if we actually got the right answer. It's going to be useful when we're debugging. It's going to be useful for short lists. It's not going to be quite as useful for very long lists. And so all we're going to do is we're going to come in here. We pass in some parameters. We print out we're testing. We take a start time. We run our sort algorithm. And we take an end time. And then we print it out. And, of course, we have flush equals true, so it comes out right away. Because we're going to run the next test, and if the next test is a really long test or crashes, we lose our data. Or at least if it's very long, it takes us a while to get our feedback. And if it crashes, then we lose it forever. So we'll do a little flush equals true there. And then if we want, we can put in this little line that checks to see whether our results were correct or not. And we'll do that when we first start out to make sure that we write our algorithms correctly. Okay, that's the main algorithm. This is our main program, right? So you can see that what the main program does is you just give it how many values you want to sort. This allows us to test our order bounds, right? How quickly does the sorting algorithm get bad as the number of elements goes up? We do a little cool prints, and then we create a sorted list, right? V is a sorted list. It's just a one-up counter from 0 through n minus 1, however many values you wanted. Makes it very easy to test. We make a copy, right? This is a slicing operation, so a slicing operation breaks aliasing and makes a copy. The copy gets put into V1. We shuffle that. We do a random shuffle, and the random shuffle creates, a jumbled up vector of the values from 0 to n minus 1. We'll create 3 copies of that just so that we can now come in and we can sort them. And we'll run our merge sort as we generate it. We'll run Python's built-in sort, which, by the way, is just a merge sort but it's a merge sort that's been written in C and heavily optimized, whereas the merge sort we write will be written in Python and won't be hardly optimized at all. And then we'll run two other sorts. One's a selection sort that we're just going to kind of really touch on quickly, and an insertion sort. And what you're going to find out is that for most cases, these are very close. Which brings us to our final little twist. What happens when your list is almost sorted? So everything is almost in the right place, but not quite. And that's what this generate local permutations does. It allows you to specify a shift, and instead of just jumbling up your input vector, we can call it down here instead of random shuffle to just move things around a little bit. So nothing's really in its right order, but nothing is all that far from where it's supposed to be either. And we're going to use that to look at some locality issues. And it's going to play a part particularly in why no one ever uses selection sort. They use insertion sort instead if they need to use a dumb sort, as opposed to something like a merge sort, which is much smarter. All right. Any questions about that? So this is our test code. We give that to you, and you can see up here that all it does is it imports time and random, and then it imports our Lecture21 sorts as sorts. That's where we're going to put all of our little algorithms, and you can see that we already have a selection sort in here. Selection sort, all it does is it goes through the list once, finds the smallest value, then it goes through the rest of the list and finds the smallest value and puts that in the first position, and then it goes through and finds the smallest value in the rest of the list and puts that in the second location. Then it finds the smallest value in the rest of the list and puts that in the third location. And so every time your list grows by one thing that's sorted into the right place, and so it just goes through, and every time through the list, it goes through from where you currently are, from the top of where you have everything sorted to the end of the list, finds the smallest value in that remainder of the list, pulls it in, and kind of makes it makes your sorted part of the list grow by one. You can see that we start out at 0. The first time through, what we end up doing is we find the smallest value, and we swap the smallest value for our 0th element. Second time through, I is 1. We swap the next smallest value in the rest of the list, or the smallest value in the rest of the list for, the first position, etc. So it's a pretty simple sort. Okay, I don't want to go into that one too much. It's in the text. You're not really responsible for knowing that one, but it is interesting to run some experiments on it a little bit later. Okay, so now, a lot of preliminary stuff. We've got 35 minutes to get through the fun stuff. By the way, just so you know, I would have you guys up here doing the dance, or at least walking through a sort if we actually were in person. So that introductory dance at the start of class was to keep you guys from having to dance on camera for me. But I always do appreciate a song and dance, so that would be good. Okay. So I kind of talked a little bit about what selection sort is. So insertion sort is just a little bit different. And because it's a little bit different, it behaves the same most of the time, but not the same all of the time. So let me throw up some numbers on the whiteboard again. You'll find this is a very whiteboard heavy lecture. I actually have another battery if we need it. Don't worry, don't be concerned if the screen goes blank, but do tell me, because I hate talking with the screen blank. Let's see. Let's throw up some numbers. It doesn't really matter what they are. 9.2, 5.37, 8.1, -1, why not? 12. How many values is that? 1, 2, 3, 4, 5, 6. Now let's throw a few more in here. 6 is good enough. We'll do 6 for now. Okay. So insertion sort starts, and in fact, all of these sorts start with the conception that any list of length 1 is sorted. So when you first start out, you assume that we have, as a sorted list, we know that we have a list of 9.2. And all we want to do is we want to take another value, the next value, and insert it into our sorted list, right, which is just this little conceptual list with one element, 9.2. We want to sort it into we want to put it into our sorted list in sorted order. So with insertion sort, the whole concept is you create a hole. So you look at the first value in the unsorted part of the list. So for that, it's 5.3, right? And you pull that out and you save it. Put it in a little holder, right? And then that creates a hole. And you look at, right, so this would be 0 and 1. So you look at 1 down from where you currently are, right? So we start out at we start out with our j, for example, equal to 0, right? We start out with j pointing here, and we compare these two values. And if this value is less than this value, then we move our hole down 1. Right? So after we do that comparison, and this is what you would have seen the people do in the dance, our hole is now moved, our 9.2 value is moved to here, and our hole has now moved to here. And now we move j down 1 more, and now j is equal to -1. Well, -1 is off the end of our list, so if j is equal to -1, whatever value is left here needs to go into that point. And now what we have is we have a sorted list of 2 elements, right? So this is conceptually a sorted list. And so we start with the next element down, right? We create a hole here. Here's our hole. These are no longer holes. These are good. Right, so we have our conceptually sorted list. We'll do that in green. This is our conceptually sorted list. We create a hole here, so we just save 7. I'll just say x equals 7. X will be our holder. We create a hole in our list. And now we look, and we say, is 7 less than 9.2? If it is, we swap 9.2 in the hole. So 9.2 goes to here. Our hole moves down to here. And now we have a 9.2 hole there. We have no hole here. Okay, x is still equal to 7. We look at 1 down from the hole. Is 7 less than 5.3? Well, no. 7 doesn't happen to be less than 9.3. Well, since this was a sorted list, we now know that we can now terminate looking here as soon as we find a number that's less than our target number. We can terminate our iterations, and we know that our hole gets filled in with our target value, right? And now we have a conceptually 1 element bigger sorted list. We create a hole with our 8.1. Right? This becomes 8.1. We create a hole here. Is 8.1 less than 9.2? Why, certainly it is. So we'll move 9.2 where the hole is. And we'll move our hole down to here. Is 8.1 less than 7? Well, no, our iteration terminates. We know that we've reached where 8.1 belongs. We throw 8.1 in there. We now have a conceptually sorted list of one more element. Let's take -1. I think at that point, well, at that point we're done. So let's just do -1 and we'll see what happens. -1, we make our -1, we back it up into here. X equals -1, right? We put a hole where -1 used to be. You know, is -1 less than 9.2? Yes, so we move 9.2 here, and we move our hole down 1. I'll save my hole from last time. Right? Is -1 less than 8.1? Well, yes, it is. So 8.1 goes here. We move our hole down 1. Is -1 less than 7? Well, yes, it is. So we will move our 7 into the hole and move our hole where the 7 was. Is -1 less than 5.3? Well, yes, it is. So 5.3 gets put here. Our hole gets moved to the end. And now we're comparing against whatever's out here in -1 land. Our counter has gone, right? It was 0 here when we compared it 5.3. Now it's -1. Well, that signals that we're as far down as we can go. So we'll just pop our -1 in here. Right, and now we have a conceptually sorted list of down to 9.2. And now the last one is 12. We pull 12 out. Right, we put a hole. But as soon as we put our hole and we look, is 12 less than 9.2? Well, no, it's not. So that terminates. We know that 12 has to go there. And we get rid of our hole and we put 12 back where it was. Okay, and that's kind of how this works. That's not kind of how this works. That's how this works. Okay, and that's what the insertion sort does. So let's do a quick insertion sort. The algorithm is here. Right, this is the algorithm. This isn't code. It's the algorithm. Let's think about this for a second, though. Well, actually, let's put it in here first. So we'll just type our insertion sort in here. Let's see. Well, we know that we want our, let's see, insertion sort. Our outer loop, right? We're going to start at the first element. Well, we're going to start any list of length 1 is sorted, right? So we'll start at 1. We're not going to start at the 0th element. It's silly to start there because we already know that that first element is, you know, in an element of length 1, it's in the right place. But we have to walk through to the end of our list. Merge sort. Sorted, the question is, what does sorted use? Sorted uses a merge sort. It uses a highly optimized Python version of a merge sort, though. Okay? All right. So this is the part where we're walking our values, right, from the start of the list, right, all the way to the end of the list. So this is where we're starting the hole off. The hole starts off in position 1, position 2, position 3, all the way down to position n-1, right? So this is moving the hole. This is the place where the hole is. We want to put where we want to look. So where we're going to look is we're going to look to the left of the hole, right, to the lower values. So J is where we're going to look when we're comparing against the hole. And now that's our starting location. And now remember we had to create our hole. So to create our hole, we'll say x equals v sub I, right? I is the position of the hole. We create the hole by pulling our value out and saving it. Okay? Why is that giving me warnings? Okay. We'll use it. Don't worry about it. All right. So now what we're going to do, right? So now we set the stage. Everything below I is sorted. We've created a hole at part I, and now we're going to take the value that was where that hole is, and we're going to find out where it belongs. We're going to find out where it belongs by moving the hole down the list until we either move the hole to the first element in the list, in which case it has to go in the first element. It's smaller than everything else in the list so far. Or we found a value that's smaller than it, in which case we can actually stop moving the hole. Right? So let's encode those. So while J is greater than or equal to 0, right? While J is one value to the left of the hole. So we're going to look to the left of the hole to see whether that value stays or gets moved into the hole. So while J less than or equal to 0, and our value X is less than our hole. Right? Our hole is going to always be at V sub J. I'm sorry, our hole is always going to be at Vj sub 1, and we're always going to be testing to the value immediately to the left of J. So this says, if we haven't found the place where this goes, if the value to the left of our value is not smaller than us, and we haven't gone all the way off the list yet, keep moving the hole. And we move the hole by filling it, right? The hole is at J plus 1. We fill the hole with the value at V sub J. And we move J to the left one step. Okay, this moves the hole. Once we get the hole moved to the right spot, then we just have to fill it in. So we say V J plus 1 gets filled in with our test value, which is X. Okay? And that's all insertion sort is. But let's do a little bit of an error bounds, or not an error bounds, a time bounds on this. Right? If we start with this, well, this is an order of n, right? This is n minus 1 technically, but n minus 1 is pretty close to n, so we'll call that order of n. Subtracting any constants or multiplying by a fixed fraction does not change order notation. So 3/5 n is order of n. N plus 10 million is order of n. 27n is order of n. Those don't actually change the value. Any fixed constant, either added or multiplied by our length parameter, does not change the order notation. So this is an order of n loop. What about this? Well, at the maximum, if our list is in exactly reversed order, every time through, we're going to have to move the hole the entire length of the sorted list. Right? So the first time through, we'll have to move it 1. The second time through, we'll have to move it 2. The third time through, we'll have to move it 3. So we're going to go from 1 to, I think at the bulk, at the very last value, if we have to move that hole all the way down through the list, well, the list at that point has gotten to be length n minus 1. So in the worst case, and we always want to think about worst case with order notation, this is going to be 1 plus 2 plus ... And that's not a plus sign, is it? Up to n minus 1. Okay? So by our basic summation formulas, what we can do is this is n minus 1 values, and the average value is n minus 1 plus 1 over 2, which is n over 2. Right? So the summation So the average value is n over 2, and there are n minus 1 values in our list. So our summation should give us, I think, come on, n times n minus 1 over 2, which equals 1/2. Well, let's put it down another line. You are not being useful to me. 1/2 times n squared minus n. Right? Okay. Order notation. We throw out any of these constants. So I paste all the way out there, and then I hit the pound sign, and it goes all the way back. There we go. We throw out the constant, so the 1/2 goes away. So that makes us order of n squared minus n. But again, we throw out anything of any lower order terms, so this is just order of n squared. Okay? So this is an n squared algorithm at its worst. The worst it can be is well, you can always make things worse. But as soon as I hit the backspace, it backspaces all the way. Okay, so this is an order of n squared algorithm. Right? All we do is we add up how many times this goes through, right? And then we multiply it by how many times this nested loop gets executed. On average, this is going to get executed n minus 1 over 2 times, this loop here. So n times n minus 1 over 2 is, well, these terms. Okay? All right, so let's see if this actually works. We'll just leave that. We'll leave those warnings there for now. I am going to do. I think I can do the insertion sort. Hopefully, we can do the insertion sort at this point. And we'll actually take out the. Oh, this is actually, this is again, these are we do run this to kind of test our code. This is below the if name equals main, so we should be able to run this. And, this is testing. We give it some real values, but we give it some minuses. In fact, this is in exactly reverse order, which is a good thing to test. We test an empty list. We test multiples in the list. We make sure that it sorts for all of those. As we go through, maybe we would want to test things like singletons, one element in the list, and so on. But that's pretty, that's at least demonstrative that this actually works. Okay? Any questions on insertion sort? I know that this is a lot of stuff thrown at you. Please take a look at this. You do need to look at these. Otherwise, it's not good enough just to have me tell you stuff. You do actually have to work with these and put some print statements in. The one thing we didn't capture here, so we do some testing. We show the testing. The one thing we didn't capture is a singleton list. Maybe v equals 12. insertion sort v and print v. So maybe we would want to do that as well. If we run that, yeah, so that works as well. So we're working pretty good. All right. So our analysis shows us that this takes about n squared over 2. We're writing about this in terms of comparisons, but it's essentially operations. You can think about that as, the comparisons are, when you're analyzing a sort algorithm, generally there's one comparison. The comparisons are what matter, quite honestly. At least that's essentially the amount of time we have to walk through. That inner loop gets executed n times on average per pass, and the outer loop gets executed n times, n minus 1 times even. So order of n squared. But that's a pretty intuitive way to sort. And I'm telling you that we can do it faster.